So today I'd like to talk about a toast-based pipeline that I've been working on for CCAT-prime. And also I'll briefly mention how we could possibly implement that in the context of CMB-INFLATE. So I'll first introduce what CCAT-prime is and what it plans to do, and then talk about the toast-based pipeline. So the telescope which is being built by this CCAT-prime collaboration is called the Fred Young submillimeter telescope. It's a 6-meter aperture telescope. And one of the instruments that will operate on it is called PrimeCam. It hosts 5 polarization sensitive modules operating at 220 to 860 gigahertz frequency bands. The instrument will also host 2 imaging spectrometer modules for line intensity mapping from 210 to 420 gigahertz. The CCAT-prime is planned to be working in collaboration with Simon's Observatory and also later on with CMB-INFLATE. The main, contribution from CCAT-prime towards constraining models of inflation would be that because of these high frequency band observations that we have, we can better constrain CMB foregrounds and further obtain good constraints on dust models and reduce bias on the tensor to scalar ratio. Some of the planned surveys for CCAT-prime are listed here in this table. What is most important, or the primary survey, is the wide field survey, which is planned to observe for 4,000 hours over an area of 20,000 square degrees. Another is the deep survey, which plans to study the epoch of reionization. Now coming to simulations of time-ordered data, I've basically been using the TOAST software framework. I will not go into introducing it again because we've already discussed that quite a lot in the past few meetings. I will briefly mention all the ingredients that go into the pipeline to generate time-ordered data. So first, we need to define an observation schedule, which is dependent on the science case that we are interested in. That also defines the scanning strategy and a focal plane. Then we define the field of sky that we would like to observe. Here, as an example, I've shown the wide field survey field of sky that is being planned to observe. And then we need to define the detector noise and atmospheric noise parameters. Since the Fred Young's submillimeter telescope is a ground-based telescope, we also need to model atmospheric noise. So here is an example. I show the power spectrum density of 1/f detector noise with a high-pass filter. And then we need an input signal template. For demonstration purposes here, I've used CMB maps as my input signal. And we then can generate TOD. In the upper part of the upper figures, I show the TOD generated for 2 detectors over a period of 1 day. And as you can see, the detector noise is slightly different for any given 2 detectors, whereas since they observe the same part of the atmosphere at any given time, there is no difference in the TOD of atmosphere between any two given detectors. And on the right top panel, I show the simulated time stream of signal plus detector and atmospheric noise. And as is evident, atmospheric noise is extremely dominant in this case. So from TOD, I used the native TOS map maker to generate maps, which is shown in the bottom panel. On the left, we have the input map, and in the middle, we have the D-striped, and on the right, the binned maps. As you can see again at map levels as well, atmospheric noise is quite dominant. This again stresses the need for us to try to simulate appropriate noise models in order to study their effects at map level. Finally, I used NowMaster to generate angular power spectra from the maps that were computed using TOAST. As on the top left here, we have the TT angular power spectrum. The red curve is the theoretical spectrum. Green is corresponds to the input CMB. Yellow is the, orange corresponds to the binned map, and blue corresponds to the D-striped angular power spectra computed from the D-striped map. Because of detector and atmospheric noise, the power spectra have a much more power in comparison to the theoretical spectra.
Vyoma, is this for one day or how many days?
This is a scan over 2 days.
2 days, okay.
Yes, yeah, continuous scan. And also I did not include sun or moon avoidance in these simulations. But that functionality also exists within TOAST.
Yeah, I guess it's not that surprising that we don't see signal only after 2 days, right? Even
yes,
after.
Yes.
And
yes,
it's actually also one detector set. I guess not full focal plane.
Yes, in this case, I'm using 14 detectors.
14, okay.
Yes, yeah. Yes, so one can generate such power spectra and study the effects of noise again. So finally, I would like to conclude with this slide here about how such a TOAST-based pipeline can fit into CMB-INFLATE. One opportunity would be that we obtain models of instrument systematics, detector response, and implement them in the pipeline. And depending on the science cases, we could also obtain input sky models from work package 3 to generate sky signal TOD and implement that again in TOAST to study different effects of noise. Yeah, thank you.
Thank you. So Ted has hand raised.
Yeah, I wanted to say this is, Vyoma, this is really awesome. And I just wanted to make a comment on the map making results. I'm sure that you probably know from talking to Rayo and others for the ground-based experiments like Simon's Observatory and CMBS-4, we sort of have an ongoing map making comparison to try to quantify the different types of techniques that we can use to mitigate the atmosphere. So in TOAST we have a bunch of different filtering techniques, so that can be applied, both a 1D polynomial filter, a 2-dimensional polynomial filter across the field of view, so essentially removing a spatial filter at every sample across all detectors. So I think it's still an open question, what combination of techniques we might want to apply for a given telescope. And of course, folded in with that comparison will be the ACT style maximum likelihood map maker that applies a correlated noise filter. So I think, it's still a ripe area for research in terms of, the best technique to beat down on the atmosphere in the map making. Some of that obviously depends on on the field of view. If you have a very tiny field of view, like the Toltec experiment, for example, at the LMT, we're working on some toast map making with that because it's such a tiny field of view, the atmosphere truly is just like a common mode signal. So yeah, I just wanted to point out that, this is a really great example of, why we want to try a bunch of different analysis techniques, and why we've added a bunch of that to toast.
Yes, definitely. And I just want to mention that the documentation has been so extensive. It's been really helpful. Yeah.
Oh, well, I would say the opposite, that it kind of is in a horrible state at the moment, but it will be getting better.
Oh, that's great. That's good to know.
Yeah, and Vyoma, if you had any feedback, you send them, because it should be very helpful to them as well, to the community as a whole.
Oh, yeah. Okay.
Yeah. Any other comments? So of course, within the framework of CMB-INFLATE, this isn't quite large scale. So we don't have halfway plate for CCAT. Therefore, we could already go down to modest multiples for recombination bump, not quite to lower L's. But I guess the intention here is that, okay, we need it for CCAT anyway, so that's a starting point, but eventually we will try to kind of try it out with inputs from the work package 1 with the work package 3 in light of more like a large angular scale mission. Then there will be some overlap with existing effort of the Lightbird toast. We should just coordinate. But at the moment, we will be looking into more in the CCAT.